working with multiple load cases, and each load case has its own constraint set and its own force set. I just started with a geometry. I go to application, pre-post. As you know, we make a new FEM simulation file. In the first step you leave the geometry like it is, and in the second step take just another solution type. You take the 101 solution but linear static with subcase constraints. That's exactly there where you also put it element iterative solver, or you can go to geometry check none. Okay. As before, you have to make a mesh. I just make this hex mesh and give the size myself by 10. I introduce a material, assign material. I just take a normal steel, and I am finished with the finite element things. I go to simulation file. In the simulation file, like before, I don't like to see the mesh, so I make it invisible, and now I see the same as before, and you have no difference until you look exactly on the subcase. The subcase has constraints and loads. So I rename the first subcase, the first load case. I say it's load case 1, and I simulate the traction on a beam. So I introduce a force type just on this surface. I'm pulling in direction X with a size of 10,000 Newton, and I have that. I do also the fixation, as you know it, just this fixed constraint on this surface, so it is fixed. That's my first load case. Now, like before, I can make a new load case called here new subcase. New subcase, it's existing here, or you could also choose it here by step subcase. Personally, I prefer to do it here in the navigator. I take new subcase, I give a name, and that's the load case 2. I'm simulating a flexion. You see it's the active one, it's solution 1 active, and the load case flexion is active, and you don't see any of the forces or constraints. If I activate traction, you see what we have done before. So I return to flexion. I introduce the force on this surface in minus Z direction, and I introduce 10,000 Newton also as flexion. I put on this side a little bit another constraint. Doing the same, I use the user defined constraint on this surface, and you see you have all 6 degrees of freedoms. The first, that's the X translation, second Y translation, third Z translation, fourth rotation about X, rotation about Y is degree of 5, degrees of 6 is Z rotation. I fix everything. As we know, in 3D the translation constraints are taken in consideration, but not the rotation, so I can leave them free. If I put something in here free or fixed, it doesn't matter, because tetraeders don't have any rotations. Be careful not to take something like rotation. It doesn't matter here with the 3D, but here displacement, you can give a displacement you want to have. I just may let it fixed. In FEM it's possible also to give a translation, not only to give forces. So it's fixed, and you see how it's represented fixed in this manner. You see every node that he is limited in translation. We have just the x cross there, so it's okay. I've done all. I let solve. I'm looking at the result files. As you could already suppose, we see traction. There is only 1/100th of a deformation, and we have inflection, 1.6 millimeter deflection. If you look at the stress here, it's a minimal stress. That's about this 6.5, or all over it's just 4 megapascal for Newton meters. If you compare it to the flexion we have with flexion, the same force provoked me here a stress going up to 150 megapascal. So you see here in this example also that flexion is really the case where the stresses are much higher. I just return and I show you here traction, flexion, and in area of that it has the own part for constraints and for forces. By the way, here you can't make a combined load case. It's not possible here, so that's a disadvantage if you want, but it's clear if there are different constraints, that's not useful to make a linear combination like we did it in the last module. That's all.